Continuing our discussion on the method of finite differences approach towards solving a variational problem, what I'd like to do right now is explain the second method that I mentioned earlier in the previous part of this lecture. Method number 2 is, in a certain sense, very, very similar to method number 1, but instead of fixing a partition along the y coordinate, we're instead going to do, in some sense, the opposite of that. We're going to fix a partition of n points along the x coordinate, or the x-axis. And just like in method 1, if we consider not actually taking this limit, but fixing a value of n, such that we only have a finite number of points, this is going to be an approximation. So this summation is an approximation of the integral of this function. Only now, because we've fixed the values of x, in this summation, all of the x values that occur in this summation, x1, x2, all the way up to xn, are constant values, are fixed values, and the y's are what are being treated as variable here. So, for instance, this expression is a function, so I'll call that function s. S is a function of y1, y2, all the way up to yn. So, what this means is that for different values of y1, the y coordinate on each one of these fixed values of x, plugging in a different y coordinate will give you a different value of this multivariable function. And because this multivariable function is an approximation to this integral, this definite integral, the idea behind method 2 is really the same idea behind method 1. What we're going to do is try to optimize this multivariable function of y1 through yn and see if we can't arrive at the correct solution to the problem that we showed via method 1. And just like before, geometrically, this is corresponding to finding the best piecewise linear approximation to the solution of our optimization problem. This piecewise approximation drawn here is probably not a very good one because it's moving very, very far away from the optimal curve. But this is the idea. Instead of fixing y, we're fixing x in method 2. Just like in method 1, what we're going to do now is go through and try to find the condition for being a local minima of this function s, or a critical point of this function s. Specifically, we're only going to look at the case of critical points where the function is very nicely behaved. So where we have all of the partial derivatives are equal to 0. We're going to see if that leads us to a useful condition. So taking the partial derivatives of this function s is going to be just taking the kth partial derivative of s, or the jth partial derivative of s with respect to coordinate yj, and setting these equal to 0. This will give us all of the local mins of this function s, as long as the function is well behaved at these points. In order to take these partial derivatives, we have to take the partial derivatives of this sum with respect to yj, and doing this, taking the derivative of this summation with respect to yj, will lead to arriving at derivative of a finite sum, which is the same thing as that finite sum of the derivative of each individual term. And luckily, these are a little bit easier to evaluate than in the method 1 case. We still have relatively complicated dependence here. However, the dependence is now, we're looking at the dependence of this f on y, so all of the y's. Remember that we took ykp to be delta yk over delta xk, or yk minus 1, or yk minus 1 over xk minus 1. So what we have here is essentially a dependence of the following form. We have, say, some function g, which depends on y. It also depends on x, and it depends on its third argument, ykp, which is, say, z. But ykp depends on all of the yks, so z depends on y. And what that means then is that when we take the derivative of g of x comma y comma z of y, we need to use the multivariable chain rule here, and the derivative of g with respect to y is going to be of the form partial g partial y plus partial g partial z times the derivative of z with respect to y. And so, taking the partial derivatives in this manner, we obtain the following. The yj partial derivative of this by the chain rule is going to be the partial derivative of f with respect to y at xk, yk, ykp multiplied by the derivative of yk with respect to yj. Plus the partial derivative of f with respect to y prime at xk, yk, ykp multiplied by the partial derivative of ykp with respect to yj. All of this times delta xk. And just like before, this is where things get very nice. We first need to simplify what some of these derivatives are. The partial derivative of yk with respect to yj is just equal to 1 if k equals j, and 0 if k is not equal to j. And the partial derivative of ykp with respect to yj is a little bit more complicated, but still easier to calculate than the method 1 method. The derivative of ykp with respect to yj is going to be 1 over xj minus 1 if k equals j, because that's the derivative of this function if k equals j. If j equals k minus 1, this is going to be negative 1 over, and when j equals k minus 1, the derivative of yj minus 1 is 1. You have negative sign here, so it's going to be negative 1. And if j equals k minus 1, then k equals j plus 1. So it's 1 over xj plus 1 minus xj. This is when k equals j plus 1, or j equals k minus 1. And it's going to be 0 otherwise. So this means the following about this summation. Instead of being a relatively complicated summation, we have that this term right here is going to simplify to just being equal to fy at xj, yj, yjp plus this summation right here, which is only non-zero at two terms. The first when k equals j, and the second when k equals j plus 1. Oops, and I forgot one thing here. Forgot to multiply through by delta xk here, which is a delta xj, because this is non-zero when k equals j. So this will be fy prime. When k equals j, you have xj, yj, yjp. This is going to be 1 over xj minus 1, which is in reality xj minus 1 is delta xj, but we're multiplying by delta xj. So this will just be equal to 1 here. The coefficients cancel out. The delta xj cancels with this delta xj. And then we have minus, because this is negative, when k equals j plus 1, you have fy prime at xj plus 1, yj plus 1, yj plus yp, j plus 1. And this is times negative, because there's negative when k equals j plus 1. But just like before, you have 1 over delta xj plus 1, or xj plus 1 minus xj, times delta xj plus 1, because k equals j plus 1 here for this term. And these are the three terms that this sum reduces to under these assumptions. And remember the goal here, we're trying to find any simple critical points of this function s, this sum function. So this is why we're setting these partial derivatives equal to 0 and seeing if we can solve and make sense of the equations that we get. So this entire thing is going to be equal to 0. Now, this gives us a slightly simpler looking equation to the one we found before, and with a little bit of rewriting we can make it look very, very nice, especially when we take the limit. Specifically, what I'm going to do is rewrite this a little bit. The delta xj is always positive, so we can divide both sides of this expression by it. We're assuming that our partition is made up of points x1 through xn, where these points are always increasing, strictly increasing. So dividing by delta xj gives the following expression. We have fy at xj, yj, yjp minus fy prime at xj plus 1, yj plus 1, yj plus 1 p minus fy prime at xj, yj, yjp. All of this divided by delta xj. This must equal 0. So this is what we get when we divide by delta xj. And at this point, we could go through and try and do a numerical solution using some nonlinear system solver to solve this system for y1 through yn. However, I've written this in this specific way right here because what I'd like to do is just show you what happens when we take the limit. we take n, or the number of points in our partition, and we take this limit as n goes to infinity. For any given point, we're going to have here fy evaluated at x, yj p goes to y prime. And I want you to think a little bit about what this entire thing goes to as n goes to infinity. The delta xj, the maximum size of this delta xj, is going to 0. But this difference right here at any point x is also going to 0 because the point xj plus 1 is getting closer and closer and closer to the point xj. So in the limit as n goes to infinity, this expression right here reduces to the normal derivative, the x derivative of the function fy prime at the point x, y, and yj plus 1p goes to y prime. And this is a very, very, very fundamental and important equation. So important, in fact, that I'm going to box this equation. This is called the Euler-Lagrange equation. Or the Euler-Lagrange ODE for the functional defined previously, so defined as the integral of f. If we accept the fact that f for fy prime, these are all functions of x, y, and y prime, we can abbreviate this equation as fy minus the x derivative of fy prime. Just a more compact way of writing down the Euler-Lagrange ODE. But this ordinary differential equation is significantly different than the differential equation that we arrived at when we did the method 1 for the finite difference solution. You remember that when we did method 1, we arrived at a first order ordinary differential equation, so a first order ODE. This ended up giving us the solution to the Beer-Hiestand problem. But what I'd like to do is relate this ODE that we've obtained right here, the Euler-Lagrange ODE, to the method 1 ODE that we got. You'll remember from before that in the method 1 we actually assumed that the function f did not depend explicitly on x. So let's make this assumption and try and see if we can't reduce what we found here, this second order ordinary differential equation, down to that case that we showed in method 1. So I'll use the color orange to talk about this case. Before I do that, though, I'll just say review from multivariable calculus. Let's say we have a function g of x, y, and y prime. So g depends possibly independently on x. It depends on y, which also depends on x, and it depends on y prime, which also depends on x. Then the derivative of something like this with respect to x is going to be the partial derivative of g with respect to x plus the partial derivative of g with respect to y times the derivative of y with respect to x plus the partial derivative of g with respect to y prime times the derivative of y prime with respect to x. Or in short, it's going to be gx plus gy times y prime plus gy prime times y double prime. So in the brachistochrone problem, the function f does not depend on x, so it makes the x partial derivative here equal to 0, which means if gx equals 0, then the derivative of this expression with respect to x is just gy times y prime plus gy prime times y double prime. And so what that means about this derivative term in the Euler-Lagrange equation is that this will reduce to just this expression right here, but with fy prime in place of g. So our Euler-Lagrange equation will become fy minus f y prime y, which is the derivative of fy prime with respect to y, times y prime plus fy prime y prime times y double prime equals 0. That's the Euler-Lagrange equation with the assumption that fx equals 0. There's no x dependence explicitly in our integrand function. And so if we multiply this entire expression by y prime, we get the following expression: y prime times fy minus fy prime y times y prime squared plus or minus fy prime y prime y double prime times y prime. So all I did here was just multiply both sides of this equation by y prime. And again, you may not see where I'm going with this, and I wouldn't blame you. This is definitely not looking much like what we got when we did method 1, or it's not looking very simple compared to method 1. However, if you think for a little bit about what this is equal to, and I encourage you to go through and do the calculation to verify for yourself that this entire expression is the same thing as the total x derivative of f minus y prime times f y prime equals 0. To show this, you would need to go through and take the derivative of the function f using the multivariable chain rule and the assumption that f does not depend on x explicitly. That's how you get this first derivative. And when you take this derivative right here, you have to use the product rule in the assumption that f does not depend on x explicitly. But when you go through and do that, you get terms that middle terms that cancel one another and directly reduce to this expression right here. And this should look pretty familiar because this is very similar to, or looking very similar to what we got using method 1 in the assumption that fx equals 0. And so this is what the Euler-Lagrange ordinary differential equation reduces to if fx is 0, or the function f does not depend on x explicitly. And this is really, really nice, especially considering what we got before using method 1. It's so nice, in fact, that it actually has the solution to this Euler-Lagrange ODE has a very special name. It's called Beltrami's Identity. Because this ODE is a very nice ODE. It's saying that the x total derivative of this expression equals 0. This is a very easy ordinary differential equation to solve. If this expression, the derivative of it is equal to 0, it must mean that the solution to this differential equation, or at least this is a second order differential equation, remember, so the first integral of this ordinary differential equation is going to be f minus y prime times fy prime must be equal to a constant c. And you'll remember from method 1 that this is exactly the differential equation that we derived using the method 1 method of finite differences. So remember, this is only holding, this ODE only holds if fx equals 0. But this is essentially re-verifying the differential equation that we solved for before. And it's incredible, I think, that these two methods are giving us the correct formulation of this problem, or the correct way for formulating the solution of this problem. So what we've seen is that method 2 is in fact a little bit more general. We didn't have to make any assumptions on the function f and its dependence on x. And this is in fact what we're going to see for the general case. This Euler-Lagrange differential equation is in fact the general ODE that has to be satisfied when we're trying to maximize or minimize a given functional. But under the assumption of no dependence, no explicit dependence on x, we see that this second order ODE is solved via a very simple method of solution. And then for a given problem, you then need to go through and solve this new ODE if f does not depend explicitly on x. What I'd like to do now is take a step back and consider a geometric interpretation of what this equation means. We're in this class going to define what a variational derivative is, what the derivative of a functional is, and it turns out that this second order ODE is intimately related to this concept of the variational derivative of a functional, an integral functional of the previous form. So I'd like to take a step back and kind of consider this equation right here, the equation that we took the limit of before, and get kind of a geometric picture of what's going on here. So let's, for a second, assume that all of the yj's are optimal. So all of the yks are optimal values except for one of the y values, yj. The picture here looks like this. So we have that for each one of the yj values, or yk values, they're all optimal except for one value right here. This idea is going to be intimately related to the concept of variation of a functional that we're going to develop in the coming lectures. The expression on the left of this equation right here was obtained by taking the partial derivative of that the sum, the approximate sum, the approximation to the integral with respect to yj, and then dividing that expression by delta xj. So we took this derivative, set it equal to 0, and then divided by delta xj to arrive at this expression right here. So I just wrote that right here, to partial s, partial yj, and we divided it by delta x. I'm going to assume that delta xj is just constant, so the width of these partitions is constant, just for simplicity's in terms of writing down what I'm about to discuss here. So this is the same thing on the left right here as the partial derivative of s with respect to yj, which is exactly the limit as delta y goes to 0 of s at yj plus delta y minus s at yj over delta y times 1 over delta x, which we can bring the 1 over delta x into this expression to write the limit as delta y goes to 0 of s at yj plus delta y minus s at yj over delta y times delta x. Delta y here being the change, this height, so the change in the function from the optimal value to the value at the approximation at yj. And then we took this expression right here and we took the limit as n went to infinity, or as delta x went to 0, to get the expression from before. So we took the limit as delta x went to 0 of this partial s partial yj times 1 over delta x, which from this expression right here is the same thing as the limit as delta x goes to 0 of the limit as delta y goes to 0 of s of yj plus delta y minus s of yj over delta y times delta x. And this is a really, really important interpretation and a very special picture. Because if you look at the shapes that we have here, we have exactly a triangle in both cases. Specifically, it's a triangle with delta y remember that delta y is the difference between the non-optimal y value and the optimal y value. This distance right here is delta y, this red line right here. And if we switch to a coordinate system, a different coordinate system around this point right here, so we sort of zoom in here and we switch to a different coordinate system where along the x-axis we plot the optimal values along this, say, s-axis right here. So this is the optimal value here, this is the optimal value here, this is the optimal value here. At this point, we're at the optimal value. At this point, we're at the optimal value. The only point where we've moved away is this distance right here. This is delta y. So this is a new coordinate system, a sort of h or variation coordinate system along the y-axis here, and along the s-axis, this point is 0, this point is 0, and this point is 0. We can see very clearly that we have two triangles right here. Each with delta x and delta x. So the area of each one of these triangles is 1/2 delta x times delta y plus 1/2 delta x times delta y, or just delta x times delta y. So remembering what this limit becomes, if it exists, this limit ends up becoming exactly that fy minus d dx of fy prime. And this is a very, very important point because essentially we can think of the variational derivative of a functional as being the limit of the change in the functional with respect to the change in area between the varied curve or the non-optimal curve and the optimal curve itself. This is a very, very interesting interpretation, so much so that it's actually defined as we can define delta j delta sigma, the derivative, variational derivative of the functional, as the derivative of the functional, the rate of change of the functional with respect to the varied area when we choose a non-optimal solution. In this visual geometric interpretation is very, very special, and I think will be very, very useful in what's to come. But I think this is a good spot to end the lecture. Thank you very much for tuning in. I hope you learned something and had a fantastic day.